Okay, so you guys all had your exam at the end of last week. The solutions for the exam for all sections have been posted over the weekend. You can take a look at those. Again, if you see that you did not get every question correctly by a long shot, please do not panic. These tests are curved, and so just wait until you get the exam back and see how you did relative to your classmates. So I will be looking, hopefully, to get you your exams back for the people who are, like you here in the room, who are in the traditional section. I'll hopefully, if all goes well, pass back your exams on Friday. And then for those of people who only are watching online, I will try to get the scores up onto WebAssign around the same time frame, so no one is waiting too long to get their scores. That's particularly important because, as a reminder, we had to cancel lab this week, so we cannot get you your exams back in lab. So again, unfortunately, there's nothing I could do about that. It's out of my hands. We cannot have lab this week. So enjoy the week off, and then I'll try to post the next homework. Actually, did I already? Can't remember. Okay, so you can work on that. Work on the next homework, homework number 6, which I've already done a significant part of, and we'll finish up here in the next couple days, hopefully. Have any questions before I begin? Yeah?
Will you be posting scores before handing the test back on Friday?
Probably not. So probably your first opportunity to get your score would be by picking it up in lecture. But the posting it online should not follow more than a day or two after that, I think.
Okay.
I just have to figure out how to wrangle WebAssign into doing it, so that's going to be the delay. I've tried it in the past, and it hasn't worked out as well as I have wanted, so I'm going to have to kind of wrangle it a little bit more. Okay, so we're starting kind of a new topic that we're going to be on for a bit, work and energy. Now, just to remind you, this was kind of like your decision tree for force problems, and I already alluded at the time that this is something that was going to be essential. So here's your cornerstone, F net equals ma, of the forces method, as we call it. It was the big subject of your first exam. So, of course, there's a whole lead up behind this, right? If you're going to use that, you have to know about individual forces. You have to know the basic behaviors of tension, gravity, friction, normal force. You have to be able to combine them into a net force. Remember, a net force is just the sum total of the forces you have. That requires something called vector addition, which can be tricky until we learned about doing it component-wise, which is very straightforward. And then, if you're lucky enough that your net force is constant, so all of your forces are constant, then your acceleration will be constant, and then you can use, of course, constant acceleration equations, which was the big 1-2 punch of first exam, right? Can you compute your own accelerations? Can you then use your accelerations to say things about displacement, velocity, time, things like that? But if your net force and acceleration are not constant, you were out of luck previously. What we have to do is develop the energy method. Now notice that if we are no longer concerned with the force and acceleration being constant, it opens up a huge possibility of much more complicated motions than we could do before. So this is really going to have a payoff. But it's going to be a slow build. In fact, if I were to visualize it, here's what it would look like. Here we have the forces method. That's something that you guys already know from exam 1 and homeworks 1 through 4. It's going to kind of seem like an uphill climb. And we're going to get to something called the work method. The work method is actually on the end of your homework number 6, your current homework. So this is homeworks 1 through 5. This is homework number 6. In the work method form, it's going to be questionable if this is an improvement on anything. It's going to be, of course, a whole other thing for you to learn. It's not going to be clearly more powerful in any way than what we did before, but we're going to find there's the promised land over here. We're going to eventually develop it into something called the energy method, which we're going to use homework 7 and beyond. And that is probably going to be your favorite method of the class. It's simultaneously extremely powerful and extremely easy to use. Okay? There's only a couple downsides, so sometimes we still need to use forces. I'll get into why that is. And more importantly, once we get there, you might question, why didn't we just do this from the beginning? This is so great. I'll point out not only there's a little bit of a downside, but this entire thing is built off the top of the forces method, so there's no way you can understand what you're actually doing if you don't understand forces first. Okay? You'll see that very quickly as we jump in here. If you don't know a force, you can't do this new stuff at all. So that's kind of where we're going with this. So let me go ahead and get started. Let's talk about work. It's a word we throw around all the time in everyday language, and yet it actually has a very precise physical definition. Okay? So, let's imagine we have a box. We exert a force on it, and we push it around. We displace it. You might say, in everyday English, pushing a box around on the floor all day is hard work. Okay? So let's try to quantify how much work is actually being done. I'm going to propose the formula for work where I take the size of my force and the size of my displacement, and I multiply them together. So let me tell you why I did that. First of all, why did I take only the sizes of those? Why did I leave off the vector hats? So these are sizes only. Well, the reason why is that the amount of work is a number. It's a scalar. Right? You often don't say that homework was a lot of hard work to the left. Right? Work is an amount. Right? So this is going to be a scalar. It's not a vector. And so for that purpose, I want to strip off the directionality of the individual vectors that I'm using. It's just as much hard work to push a box to the right as to the left. Right? So that's one thing. The second, why did I choose to multiply them? Well, choosing to multiply them means that you can do your work in several different ways. I chose to multiply them because the product makes a lot of sense. Let's suppose that I exerted a large force over a small displacement. That could be the equivalent amount of work to a small force, but exerted over a very large displacement. This is kind of like your sprint approach, and this is kind of like your marathon approach. So think about what you're doing when you're sprinting. When you're sprinting, you're exerting a lot of force with your legs, right? But it may only be for a couple hundred meters, right? Sprints are short. There's going to be some kind of equivalence to if you run a longer race where you're not running nearly as hard, right? You're not exerting nearly as much force with your legs, but you do that over a very, very long distance. So you can see that the product makes a lot of sense because it means that you can do more work either by exerting more force or by doing it over a longer displacement, or of course if you want to do a lot of work, make them both bigger, right? So you can do more work either by exerting more force, doing it over a longer displacement, or both. So that's my first guess at the formula for work, and I hope that makes intuitive sense to you. And in fact, that is correct enough to get the units of work. So whatever I'm going to do to modify this after my first guess is apparently not going to affect the units. What are the units we usually use for force? Newtons. And how about for displacement? Meters. So work is measured in Newton meters. We call that a joule. Capital J. So it's yet another composite unit. It's not its own new unit, it's just an abbreviation for a clump of units. That's simpler. Now let me remind you that a Newton itself was such a thing. A Newton, right, force is units of mass times acceleration. So a Newton was a kilogram meter per second squared, and now I'm multiplying it by an extra meter. So if you wanted to express a joule in terms of the fundamental units, it's a kilogram meter squared per second squared. So remember on the first day of this class, we said that all of the units that we would see subsequently are going to be combinations of kilograms, meters, seconds, and angle, radians. And this is just a particular combination of kilograms, meters, and seconds, and we call it a joule just because we don't want to write all that every time we want to talk about work. Okay? So that's the units of work measured in joules. And I only need to do one modification to this formula before I move forward. Now, one of the things that is a little bit weird about this equation is the fact that it seems to suggest that if the displacement is 0, the work is 0. That seems to kind of be antithetical to the way we use it in everyday language. So for instance, if I sit here and I push on this wall all day, right, I might say that's a lot of hard work, pushing on this wall all day. But if the wall isn't moving, it's not displacing, I have to call it 0 work. So obviously this is something that seems to be at odds with the way we use the word in everyday language. Now I'm going to resolve that paradox. It turns out that there is no problem at all. But I'm going to resolve it for you later once we understand a little bit more about what work is. But for right now, I want you to kind of understand that if there's no displacement, there's no work. Now, how does that mean that I have to modify the equation? Well, let me suppose I have that same crate. I can, of course, push it around on the floor like this. In fact, for someone as tall as me, that's probably how I'm more likely to push something around. I have a problem stooping over, so I'm going to probably exert, kind of lean on it at the same time, right, as I push it. So I can still displace it to the right, but the force doesn't happen to point exactly that way. How can it slide toward the right when I'm pushing it at a downward angle? Well, of course, my pushing force isn't all there is, right? There's normal force, gravity, maybe friction. So I can ask about the work that I do without it necessarily being that my force is all the force, okay? So here's what I'm going to say. This force that I'm exerting can be broken into two components. I'll call it F parallel and F perpendicular. And when I say parallel and perpendicular, I'm really referring to relative to the displacement. So these are both relative to the displacement. So any force can be broken into components, one of which is potentially along the line that the displacement is on, and the other which is completely perpendicular to it. And here's my argument. If I only had F perpendicular, right? If only I was pushing directly into the surface, the box wouldn't move, right? And so what I'm forced to conclude is that this component, it does no work. that component is just along for the ride. If that were the only force, there would be no displacement. I can therefore conclude that that force component has no responsibility to work. In fact, my only correction to my previous formula will be that it's actually the parallel component that's responsible for the work. And so, if I go back over to my first guess, I can see not only was this a good first guess, but it happens to be completely correct for the way I drew this. Because you notice here that the perpendicular component does not exist. So F parallel is the whole force. So this was completely correct because I happen to exert all of my force parallel. If I don't, then only the parallel component is actually useful for doing work. Okay? Now this is not only a good guess, this is completely correct and general. So what I'm doing when I'm calculating work is I'm taking a force and figuring out what component, if not the whole thing, what component is going to help me with my task. So it's going to be with the motion, or it could be against the motion. Okay? But the point is it's acting along the same line. It's not completely independent. It's not perpendicular. I throw that part away. This is the most correct in general. Now I'm just going to make a cosmetic change to it so it becomes more easy to plug and chug it without thinking. So I'm going to pick this angle to be theta, and then F parallel is F cosine theta. Now, you might question if that's an improvement, because if I'm going to try to work a cosine or a sine into a formula permanently, you are right to point out, hey, cosine or sine is in the eye of the beholder, right? It depends on how you break up a triangle, right? For instance, if I were going to go over here, and I were going to break it up like this, first down, then over, and I was going to use the angle phi, right? Then the parallel component would be F sine phi. So then I should be using the sine instead of the cosine, right? So how do you make sure that you're using theta, and therefore cosine would be appropriate, and that you don't accidentally use phi, where a sine would be appropriate? Well, theta is actually a special angle, and phi is not. Let me tell you what's so special about theta. If you take the displacement vector, and you put it tail to tail with the force vector, then the angle between them is not phi, it's theta. Okay? So you can hopefully see if I take this vector and this vector, and I put them tail to tail like this, the angle between them is this angle. So this is the agreed upon way to measure the angle between two vectors. So I should write this down. So we want to measure the angle between two vectors. We need an agreed upon way of doing that. The agreed upon way of measuring the angle between two vectors is to place them tail to tail. So you see that I've done that. They are tail to tail, tail to tail. Now this is not to be confused with when we're adding vectors together. We did that head to tail, right? Remember that? I think you even tried that on the force table lab, right? You drew them head to tail. We're not adding these vectors. In fact, I should point out these vectors, it's not even possible to add them together because one's a force and one's a displacement. You can't add two things that are different. It's like adding an apple to an orange. What does that get you? If you add an apple to an apple, you get 2 apples, right? But what's the sum of an apple and an orange? Doesn't make sense. It's like adding a meter to a second. It makes no sense. We're not adding these. They're not even addable. We're just coming up with a way to measure the angle between these because it's useful to us. We put them tail to tail, and we measure the shortest angle between them. The shortest angle. So, of course, we measure that angle, not the angle all the way around the other way. And so this angle can span anywhere from 0, where the 2 vectors are pointed exactly the same way, to a maximum of 180, when they're pointed exactly opposite. And that is it. That is the entire range of angles that are possible. Again, you have 0 degrees when they're pointed exactly the same way. It can grow. It can be up to 90. It can be as big as 180 even, right? So that's a 180-degree angle. But it can never be bigger than that, because if you start to make it bigger, you should be measuring the shortest way, so that angle is actually closing again. Okay? So, in my equation, my work is going to be, and let me rearrange these, they're all just multiplied, so the parentheses are silly and pointless, as is the multiplication order. Here's my final equation. This equation right here is designed to maximize how quickly you can compute a work. It's meant to be plug and chug. What you have are the sizes of these vectors. So they have to, of course, be sizes, that's positive. Then you don't have to worry if it's cosine or sine in the equation. It's always cosine if you identify the angle in this prescribed way. So you take the force and displacement, you put them tail to tail, and you measure the shortest angle between them. Okay? And that will get you the work. It's basically this. It's keeping only the parallel component, but it's supposed to save you some SOHCAHTOA-ing, as if you're not already sick to death of it. We do it once, so we never have to do it again. So we identify the right component, we have it be a cosine, and then we have to follow certain rules for how we define how the angle is going to be measured. Are there any questions so far? Okay, so that's meant to be just kind of a simple way of computing work that is the minimum hassle. I want to take a chance here to explore the different possibilities of what could come out of this equation. We already said that the angle could range anywhere from 0 to 180. And so I want to pick there's several different categories there. And I want to draw an example of each. So we could have something like this, where the force and displacement makes an angle that is less than 90 degrees. That's one possibility. We could have that the force and displacement make an angle of exactly 90 degrees. Or the third category is it's somewhere bigger than 90 and up to 180. These are the different possibilities. So let's work out, in each case, what is it that happens? Well, cosine of an angle between 0 and 90 is positive. So what does that mean about the work? Well, of course, the force and displacement don't have any modifications to make. So if cosine is positive, the work is positive. What's cosine of 90? 0, so what's the work? 0. That one, by the way, we already expected, right? If your force is exactly perpendicular, then we said it should do no work. But cosine of an angle between 90 and 180 is actually negative, which means that that will be directly given to the work. So the work is negative. So what I'm pointing out here is that the cosine term will control what happens with the work. If the cosine term can be plus, 0, or minus, then the work itself can be plus, 0, or minus. So, this is strange. The work can be negative. The work can be plus, 0, or minus, but remember, it is a scalar. It's not a vector. It's a number. So, it does not have any directional content at all. Now before, we were saying plus and minus means like along the plus axis or pointing along the negative axis, right? That's not what this is. What is the meaning of this? Now if this seems confusing, then I'll chalk that up to a good thing, because it means that the entire first exam you got what plus and minus meant, right? Plus and minus is directional relative to an axis. That's a good thing. But let me point out, before you ever heard of a vector, before you ever got to this class, there was still such a thing as a negative number, right? If your bank account is showing a balance of negative $5, it has nothing to do with $5 to the left, right? So it's possible for a number itself to be negative, and the negative has nothing to do with direction. It has to do with something else, okay? So, let's figure out what it does. What does it mean? What does it mean when a work is positive or negative? Well, I think sometimes when you want to go forward, you have to take a step back. So what I'm going to do is I'm going to superimpose on top of this, even though I just made a big stink about the fact that we want to do the SOHCAHTOA once, so we never have to do it again. Let me superimpose the force components on here. So let's start with that. Now we know the perpendicular component is useless for work, but I want to point out that the parallel component is with the displacement. So what do you think generally would happen if something's moving in a certain direction and you are pushing it the same way? What are you going to do to it? How? Move it how? Yep. And what happens when you push on something in the same direction it's already going? It goes faster, right? So you're helping the motion, right? You're pushing in the direction it's already going. So I'm going to say that there's some connection with the work being positive and trying to speed this thing up. So there is some connection between positive work and trying to speed it up. Okay? Now, you might wonder, why do I say trying to? Well, remember, this is one force of potentially many. Just because this one force wants it to speed up doesn't mean another force might say, no, we're slowing it down. If it was up to this one force, it would speed up, okay? Because you're helping the motion, right? You're pushing it in the same direction it's already going. There's some connection with trying to speed it up. Now this is the point where oftentimes two wrongs make a right. People go, oh, look, positive work. That's like positive acceleration is speeding up. Except, of course, that's not correct either, okay? So let me point out that if your velocity is negative, your acceleration is negative, you'll still speed up, right? So it has nothing to do with direction, okay? So that would be a case of speeding up, but again, positive work has nothing to do with positive acceleration. In fact, at this point, you hopefully know that negative acceleration can make things speed up too. So the positive on work has nothing to do with a direction. Going over here, well, of course, this force neither helps nor hurts the motion. This has no effect on the speed. So there is some connection between the work being 0 and this particular force not affecting the speed. It has no component with or against the motion. It has no problem with the motion you have. In fact, it does no work at all. Now that's not to say the force doesn't exist. I'm not saying the force is 0, I'm saying it does no work. This force still does serve a function. I like to call these guiding forces, or a deflective force if you like. It's not that the force doesn't exist, it just doesn't change the speed. One prime example we saw of this was when we just did circular motion, right? Centripetal force. Centripetal force is a name for a force when the required amount of force to go in a circle, provided by real-world forces. So, for instance, you can have a tension or gravity or something which is guiding this thing in a circular path, but it's not making it go faster or slower. It's simply changing the direction of motion. It's deflecting it into a circle instead of allowing it to go in a straight line. It's guiding it in a path, but it's not changing the speed. There is a connection between work and speed change. And we're trying to figure out what is it. And by the way, it is speed. It's not velocity, right? So it's okay to change the direction. Force can change the direction of the velocity. But what we're talking about now is going faster or going slower. If we go to the final case here, you can see that this force has a component against the motion as well as a perpendicular component we're less concerned with. So here what you see is that there's a part of this force which is acting against the motion. So if it was up to this force, you would slow it down. So there is a connection between negative work and trying to slow down the object. And we don't know exactly what it is yet, but there's got to be some connection there. If your force is pointed more than 90 degrees from your motion, it's more against it than with it. And so it's going to hinder your speed more than it helps your speed. And the only reason I say trying to slow down here is, of course, this is one force out of potentially, 100. So it doesn't necessarily mean the object actually slows down. It's just that this force would want it to. This particular force would want it to. Okay? So again, this is a stage where someone says, oh, negative work, that's like negative acceleration. It's slowing down. Again, let me remind you that negative acceleration can make you speed up. Okay? So this positive 0 or minus in the work has nothing to do with direction. This is a number. It's our first negative number that can be negative, and it's got something to do with speed change, and we have yet to figure out exactly what it is. Okay? So that's the next order of business, of course. This is all well and good, but it's a computational dead end at this point. Once you have work, what do you do with it? We don't know yet. I wouldn't give you this just to have you compute something that doesn't give you any further problem-solving ability. It turns out, of course, once you figure out what your works are by all your forces, you can do something with it. So that's the next order of business. Are there any questions before I do that? Yeah?
So what's the meaning of the positive or negative?
We're going to figure it out. It's got something to do with this, right? We don't know yet exactly. We're just about to figure that out. And that comes with figuring out what work is going to get you, right? What does work do for you? Are there any other questions? All right, so let's do it. Next thing that comes in, this is where work becomes not a dead end, it becomes a means to an end. We are going to introduce the work energy theorem. the work energy theorem tells us that work has an intimate relationship with a quantity called energy, which you may have heard of. Okay? And so what I'm going to do now is try to derive for you the work energy theorem. This is going to be a little bit hand-wavy because you can't really do this properly unless you have some more advanced mathematical tools. So I'm going to write down a few assumptions as I go that aren't really truly necessary, but allow me to proceed. So let me start with this line. I could find the network that's done on an object if I add up the works of the individual forces. You probably agree that if you have 17 different forces acting on an object, you can't just pick one, compute the work by that, and expect to have anything useful if you ignore the other 16 forces, right? So whatever we're going to do, we have to account for all the forces. They all can do work, and the network is actually going to tell us something about what the object does or how it behaves, right? You can't just cherry pick one force. You have to include them all. Now, that'd be one way to get the network. The other one would be kind of cheating, so to speak, because if someone gave you 17 forces, you can always cram them into one force. We call that usually the net force, right? The net force is basically all of those forces already smashed into one. So you could also get the net work by cheating, doing a vector addition, getting the net force, and then computing the work from just that, right? That'd be defeating the purpose, by the way, because the whole purpose of this method is we don't want to have to do vector addition anymore. That's going to be one of the most awesome things about it. So it would be silly for you to bother with that, but it's going to help us here in the derivation to see things into the perspective. So, a couple things about this. First of all, I wrote this. Second of all, let's look at the angle between, so here's I'm going to put a list of suppose this is true. These are going to help me with my derivation. I'm going to suppose that my object starts from rest. Now, if an object starts from rest, and I exert a net force on it to the right, which way is it going to go? To the right. I mean, I pull it, it comes with me, right? So if that is true, then the angle between the net force and displacement is going to be what? Less than 90, specifically exactly 0, right? I pull it, it comes with me. Now, that is certainly not guaranteed for any individual force, right? That's why we had to account for all the possibilities here, right? No one force is guaranteed to have any particular relationship with displacement because there could be a bunch of others. But net force, different story, right? The net force is already all the forces, and if something starts at rest and you pull on it, you have to move in the direction of the net force. So that allows me to plug in cosine of 0, which is plus 1. So that's one thing. The other thing, the net force is mass times acceleration. That's always true, by the way. So this whole method does, of course, it's just built on top of the forces method. All right, so what do I have now? Well, okay, not much yet. And by the way, if you're wondering, how do I know where to go next? It's not easy. Okay? Trust me, even though I seem to be plugging in almost random things, that we're going to get somewhere eventually. Okay, so not seeing why I'm doing the next step, but yeah, okay, I don't know why you're doing that, but that seems okay to me, right? don't feel bad, because even though Isaac Newton almost single-handedly came up with almost everything in this course, work and energy was something that he did not figure out. This came along a little bit later. Okay? All right, what next? A times delta x. That rings a bell. I've seen it before in a formula. Does anyone remember where you've seen A times delta x?
Find out velocity.
One of the,
Vi plus A.
yeah, one of the constant acceleration equations, right? Remember that? So that equation looked like this. V final squared equals V initial squared plus 2A delta x. There it is, A delta x, right? So I'm going to suppose that I have constant acceleration so that I can maybe use that. So you can do it, and you will get whoops. You can get that. And that's my work energy theorem. You might look at that and go, what? That's it? Okay. Now I'm here to tell you that some of the assumptions that we made are not actually necessary for this to be true. In fact, none of them are necessary. So I suppose this because we didn't have the math to show that these aren't actually necessary. You don't need to start from rest. You can start any speed you want. You don't need to have constant acceleration, which, by the way, is good because we wanted a method that doesn't require it. And I should mention also that these v's are the entire speed. So when we say v here, it doesn't mean just x or y, it's the entire speed. So v is the speed in its totality. Now you may look at that and go, that doesn't look like much at all, but let me explain what we have here. Let me write it out like this. So this right here is the work energy theorem. Now, what are we looking at? Well, it tells us that the net work apparently tells us about the change in this quantity, whatever this is, 1/2 mv squared. It tells us how it changes. It's a delta between what it is at the end minus what it is at the beginning. This quantity has a name. It's called kinetic energy. Okay? So let me go, I guess, over here. Clear a little space. This is called kinetic energy, KE. KE equals 1/2 mv squared. What is it? It's the motion you have, or sorry, it's the energy you have due to your motion. It's motion energy. Because you're moving, you have energy. Let's take a look at the equation. It says if you go faster, you have more energy in your motion. Hopefully you believe me, right? If you're driving in your car at 50 miles an hour, you have more motion energy than if you're going at 2 miles an hour. How fast you're going matters. By the way, it's proportional to the square of the speed, which means that if you go twice as fast, what does that do to the amount you have of motion energy you have? You you go double the speed, what happens to the kinetic energy? 4 times, right? If you triple your speed, what happens to your kinetic energy? 9 times, right? So that's one ingredient which you hopefully expect would be in motion energy, right? How fast you're going. But there's a second ingredient, which is of course the mass. And hopefully you believe me that mass should matter too, because if you talk about a car going 50 miles an hour, that has more energy than a mosquito going at 50 miles an hour, right? It's also about how much mass you have. Notice, by the way, that kinetic energy is directly proportional to mass, which means that if you double your mass, what happens to the energy? Just doubles, right? Okay? So those are the 2 ingredients in motion energy. By the way, notice that this quantity has to be positive. Half, mass, that's positive. Speed is positive. Squared is definitely positive, right? So the least amount of motion energy you can have is 0. And then, of course, that's when you're at rest. And then you can have some more, right? If you're moving, and it doesn't matter if you're moving to the right or to the left, you have more motion energy than you had when you were at rest. So this is greater than or equal to 0. But when we go over to the work energy theorem, what we find, the work energy theorem tells you, that is it in its most condensed form, when you have work, it changes your motion energy. Okay? And by the way, that suggests that, of course, the units for kinetic energy are also joules. The units for work and energy are joules. Work simply tells you about the change to energy. So to give you an example, let's say KE final minus KE initial. Let's do some examples. Let's say you start off with plus 5 joules of motion energy, and then you go faster, so now you have plus 7. So what's the delta? Plus 2. The plus, of course, indicates simply an increase, right? When you have a delta that's positive, that just tells you the quantity is getting bigger. It tells you that the number at the end is a larger amount than the number you started. Let's say you ended up at 7, but you also started at 7. What's your delta? 0. I'm not saying that you have 0 kinetic energy. I'm saying your kinetic energy didn't change, right? It started at 7, it ended at 7, right? So this indicates no change, right? That's what the delta of 0 means. And finally, let's say you ended up at plus 5 joules, but you started at plus 7. Now notice, those values are both positive, right? In fact, we just got through saying kinetic energy has to be positive all the time. But what's the delta? Negative 2 joules. The negative simply means that this quantity decreased, right? It doesn't mean that the final or the initial value was negative. It's simply saying that the value at the end was smaller than it was at the beginning. And here we finally solved it. We have said that there's a connection between work and speed change. And now we have simply made it more formal. What does work do? It changes the motion energy. So we can go back over here and modify these guys. We said that positive work is like trying to speed it up. Well, now we can say, when you have positive work, it adds motion energy. So the environment, this particular force, is adding energy. It's adding motion energy to the object. It helps the object along the direction it's already going. When the work is 0, it has no effect on the kinetic energy. it neither adds nor subtracts motion energy. And when the work is negative, it removes kinetic energy. So now, we understand on a more formal level what it is that work is. When a work is plus, 0, or minus, it's basically telling you how it's operating on the bank account of the object's energy. When it's a plus, it's a deposit. When it's a minus, it's a withdrawal. So we're going to start balancing our checkbook here because the various forces, some of them are going to put in motion energy, plus work. Some of them are going to remove motion energy, negative work. And we balance our checkbook by looking at all the different forces either putting energy in or taking energy out, and we'll figure out what's our balance at the end of the month. So we'll do some problems on this on Wednesday.